Hi there and welcome to week 12 for GIS and spatial stats, and this week we're looking at spatial interpolation. And spatial interpolation is essentially where we have a point process or a point pattern, so we have the location of points in some region, and not only do we have their location, but at those locations we have sampled something, so we have a measure of some value. Okay, and what we want to know then is we want to know what the corresponding measure will be at other points that we haven't sampled. So essentially we need to interpolate from our observed locations to the new location. And typically the new location is everywhere else, right? So we want to know what that measure is that we've measured at just a small number of points across the region is everywhere. So examples might be soil composition. So, you know, at a bunch of locations across an area, you sample the soil and put it through some machine that tells you, the breakdown of the products in the soil, and you then want to infer what those proportions of the different products are across the entire region that you're looking at. Geological deposits is another one. Measures on anything that is located in a particular position, so houses, animals, people, and so on, is a useful thing to do as well, right? You only sample a few people in some locations, and now you want to, whatever the characteristic that you measure on those people is, you want to infer that in places that you haven't sampled. And the key idea behind it is that the measurements that we take in different locations will be correlated, right? And that points that are close to each other will tend to have values of that measurement that we're taking at those points that are the same, simply because they are close to each other. Okay, so essentially we would expect some autocorrelation, if you like, i.e. correlation induced by the spatial distribution of points. This is similar to the autocorrelation that we get through time. Right, so if you look at taking measures over time, then the measures that you take close to each other in time tend to be closer to each other because the time that you took them is close to each other. Right, so if you look at the weather, for example, right, today's weather is more similar to yesterday's weather than it is to the weather 3 weeks ago. Right. So the same thing happens in space. Right, so measures that are taken close to each other tend to be similar. And so we need to take that into account when we do our interpolation. And we're going to be covering 3 methods. There's lots of different methods for doing spatial interpolation. We're covering just a few of them. The first one we'll cover is inverse distance weighting, where essentially we interpolate using a weighted average with across the locations that we've sampled, and the weights are just proportional to 1 over the distance to those locations that we've sampled. Then we'll look at Kriging. 2 types of Kriging, simple Kriging and universal Kriging. The difference between them is that with universal Kriging we have some spatial covariate that we can use to help infer the spatial trend. Simple Kriging, we just use the values in the observation locations. So the example that we're going to use is on heavy metal concentrations in topsoil in a place near a river, the River Meuse, near the village of Stein in the Netherlands. And this is quite a famous data set. It's in the SP package. You can grab the data there, and it contains concentrations on a bunch of different heavy metals, and we're going to be looking at just one of them, which is zinc. And the measures vary a great deal, and so we're going to look at them on a log scale to sort of compress the skewness of that data. And you can see when you look at so we have essentially a floodplain here, which is, the river goes around this corner, but if there's lots of water coming down, then it can flood over. And you can see here that the lighter colours, which is the higher zinc concentrations, tend to be close to the river, while the lower concentrations tend to be further away. So there seems to be a correlation here, or an underlying spatial trend that has something to do with the distance from the river. And we'll be looking at that when we look at universal Kriging. And the other thing you notice is that things tend to be correlated, right? So the darker colours tend to be next to other dark colours, and the lighter colours tend to be next to other light colours. And it's hard to know if that's part of the spatial trend or just due to proximity. It's probably a bit of both, right? And the goal is to then estimate the zinc concentration across the whole region, and so we have a grid of locations here across the region that we wish to interpolate to. Okay, so when you're doing spatial interpolation, you have a point process or a point pattern where you've got a measurement at each point, and you want to infer what that measurement is at a bunch of other points. Okay. So the first method we'll look at is inverse distance weighting. The idea being that we can estimate the measure at a new location, x, using values from nearby locations, and we weight them in proportion to the proximity, right? So observations that are close to the new location that we want to interpolate to, we will weight them more than observations that are further away. Okay, and so to do that, we use the distance between our new location x and our sampled locations x sub I, so that's the distance here, down in this expression here, so the two bars just mean distance. Okay, it could just be the Euclidean distance, or it could be any distance measure really that we want to use. So just the distance, it could be, if you were using latitude and longitude, it could be great circle distances on the sphere or on the ellipsoid of the Earth, and so it's 1 over that because we want increasing distance to be down weighted, so we want the weights to be lower, and we raise that to some power to control just how much the longer distances are down weighted, right? So if the power is high, then we're going to take that distance and raise it to a big power, so it's going to get that distance will get very large, and so it's 1 over a very large number, which is then a very small number. Whereas if the distance is small, then after raising it to the power, the result is a bit smaller, and 1 over something that's a bit smaller will be a bit bigger, right? And so when we have these weights, they don't add up to 1, so we normalize by dividing by the sum of the weights, and then it's just a weighted average. So this is just a standard formula for a weighted average. Okay, we just take the weight, multiply it by the measure, add them all up, and normalize by the sum of the weights. Okay, if all of the weights were 1 over n, right, then they would add up to 1, so that would go away, and this would just be an average then, right? It's just 1 over n sum of zi, which is the average. So in this case, we're not just averaging, we're doing a weighted average. Okay, so the power p controls how quickly the influence of points that are far away sort of drop off. Okay, so small values of p, so p less than about 2, the distant points will have more influence, and large values of p, distant points, will have little or essentially no influence. And p equals 2 is often about right. So it's sort of, we assume that the influence of points drops off with the squared distance. This tends to work for lots of physical processes, for example, because diffusion is approximately proportional to the area, which is approximately the distance squared. Now to do this in R, we use the IDW function, short for inverse distance weighting, which is in the GStat library. Now one thing to watch is that there's also an IDW function in the SpatStat library. So if you've loaded both of those libraries, which function gets used will depend on which one loaded last. Right, so if you load GStat first, it'll load IDW from GStat, and then you load SpatStat on top, it will also load IDW and override the previous one. So if you get errors when you run IDW, some odd error that perhaps isn't completely obvious what it means, it might just be because it's running the SpatStat version and not the GStat version. So to get around that, you can just put GStat : in front of the IDW to force it to come out of the GStat library. Okay, I talk about that a little bit in the workshop. Right, so IDW, we then have a formula. The formula always takes the same form, so (1), which just means that there's no trend at all. So the IDW command cannot do a trend, but we'll see later on with universal Kriging that we can add a trend. And then we just have the variable that we're interested in. So in this case, it's log zinc. Then we take a locations spatial object, and so this can either be an SF object, so a simple features object from the SF library, or a spatial object from the SP library. Either will work. Then you have a new data set, which should also be a spatial object, which basically represents the locations that you want to interpolate to. So these are the locations you have measured zinc on. These are the locations that you don't have any measure of zinc, but you would like a measure of zinc. And then you have the power.
By default it's set to 2, but you can play around with it if you wish. And that will then give out another spatial object which is equivalent to this one. So it'll have the same locations that are in this one, but it will also have 2 extra columns, and the 2 extra columns that it has is var1.pred, which is the predicted measure, and var1.var, which in this case is unused. It'll just be set to NA, so it's a wasted column if you like. We'll see why that is later on. So you can take your var1.pred and that'll be your predicted log zinc at the new locations. So here's an example. So we use that exact same code that I had before there. I'm saving it into the Muse IDW spatial data frame, and then I'm mapping it with GeoMSF with the ggplot library. You could also just plot this, and it would use the SF library for plotting, and it'll give you a similar looking plot, right? So you can see here that that essentially we get what we would expect, right? So the yellow, the lighter colours are where we have observed higher concentrations of zinc, and the darker colours are where we have observed lower concentrations of zinc, and in between we've just interpolated. Okay, so you can see it's just sort of smoothing essentially that surface. If we change the power, so if we reduce the power down to 1, we get essentially more smoothing. Okay, and the reason is that at each location here, all of the points, instead of so if you look at this location here, for example, this point way up here will be contributing to this point just in proportion to the distance, whereas back here it would be contributing in proportion to the distance squared, which of course 1 over the distance squared, which is a much smaller number than 1 over the distance. Okay, so P smaller gives you more smoothing, P larger tends to give you less smoothing, so everything becomes more localized. So you can play around with P. It doesn't have to be a whole number. You can put 0.5 in there or whatever you like. Okay, there's some suggestion that you could optimize what that power is for a particular surface, but we're not going to look at that in this course. Right, so that's where we have inverse distance weighting. So it's a nice, fairly simple method to understand. Kriging is a little bit more complicated. And the difference between the two essentially is that the weights that we use in the weighted average for inverse distance weighting are basically the same all over the region. They only depend on the distance from the point at which you want to interpolate to the sampled points. And as long as that distance stays the same, a point that's distance d away will always have the same influence. So essentially it's kind of like global smoothing. The weights are all defined purely based on the distance of points away. So if you have lots of points in an area, in a location, that are all close, then they will have the same influence as if you're in a different location and there's only one point that's similar distance away. Right, so if you're in a very sparse location, your contribution will be from only a few points, but the weights will be the same as if you're in a very dense location. The weights will still be the same, and that doesn't necessarily make sense. You may want, if the points are dense, then you may want to only look at a very small neighborhood of the location, because you've got a lot of data there, so you shouldn't really be using points that are far away because you've got so many of them. You're going to be essentially over smoothing. So Kriging allows the formulation of the weights to adapt to the local changes in the intensity of the point pattern, right? So it can adapt to both changes in the values of the point pattern and changes in the location of the point pattern. It's still just a weighted average. It's just that weighted average can take into account the sort of the local structure in the data. So it's a bit like adaptive kernel smoothing versus fixed kernel smoothing. Okay, it's kind of the same sort of concept. It's implemented in a much different way, but the same idea applies. So to do this, what we need is some concept of how the values that we're measuring at each location vary depending on the distance between observations.
So if you like, what we want to do is we want to take the variance in two measures. So we want to take each pair in our pair of observations, and we want to see how different is the measurement at those two locations. So how different are the values that we've measured, the logs and concentrations, compared to their distance. Okay, and we want to build a model that allows us to describe that variation in terms of the distance so that we can then use that model to project to other points. Okay. So we use a variogram for this, which plots this here, which is basically half the squared difference in the measure between pairs. The half here isn't really that important, it's just a scalar. You can drop that out, it won't make any difference really to the result. It'll just scale everything up a bit. But we plot this against the distance between pairs. So for every pair of locations, we compute the squared difference in the values and the distance. And then we plot one versus the other. Okay, so here's a plot for the Muse data, just for the distances 0 to 1500. Okay, and as you can see, there's a lot of pairs here, right? So in the original data, I don't know how many observations there are, but you can sort of see that there's quite a few, right? There's probably, 100 or so. And so, number of pairs would be about 10,000. So there's a lot of things going on, and it's very hard to detect any trend here. So what we typically do is we typically break the distance into bands, and we average the gamma here within each band, and similarly average the distance between each band, and just basically to reduce the size of the data set so we can see the shape of the trend. Okay. So you can see here that at small distances, gamma is close to 0 essentially, and at large distances it sort of increases and then stabilizes. Okay, and that sort of makes sense. This is often what you end up seeing, in that essentially what it's saying is that the gamma is close to 0 at small distances, so there's very little difference between observations when they are close. So there's not much variation between observations when they are close to each other, and the variation increases over some distance and eventually plateaus. Okay, and many scenarios will result in this sort of curve. Sometimes it'll jump around a lot more depending on how many data points you have. We can do this using the Variogram function from the GStat library, and it takes that same formula that we used and the data set that we want to take it from. And that will essentially just plot these points here. Now, once we've got the observed variogram, what we need to do is fill the gaps. So we need a model that fits this trend. Okay, and there's a large number of variogram models that have been developed for many different scenarios, and some of them are here. There's a few more than this, and you can see that many of them have a sort of a fairly similar shape, where they start at a low value and increase. Okay, and they just sort of differ in sort of how that pattern works. Okay, the most useful ones tend to be the exponent, in my view anyway, tends to be the exponent, exponential, the spherical pattern, and perhaps also the return. But you can see that many of them are the same. So the circular one and the spherical one are very, very close to each other. Okay, it's just I think this one is a little bit sharper here than this one, and so on. Okay, but there's many different types. This is a periodic one where you expect the variation to sort of increase and decrease depending on how far you go. So that's where you have a repeating pattern through your region. Perhaps a periodic one might be appropriate, and you can also combine them together. And each of these models typically so they specify, so the model, exponential, spherical, Gaussian, return, and so on, that defines the overall shape, but we need to fit that shape to the data that we have. Okay, so you can see here that these all go up to 1, right, which isn't what we want for our data. Our data only goes up to about 0.5 or so, right? So we've got to scale them, we've got to shift the distance scale, we've got to shift the height scale, and so on. So there's basically 3 parameters that that govern fitting the shape to data, and that's the nugget, which is essentially the y-intercept. So that's the gamma value when the distance is essentially 0. So that's capturing the variation in points that are very close to each other, okay, which is basically sort of the variation in the measure taken repeatedly at the same location, if you like. So the measures that we'll take will often be a little bit noisy, and so they'll have some variation, and that'll be captured by the nugget. Then we have the partial sill, which is basically the value that we flatten out at. So the value that gamma takes as it starts to flatten out. So we saw over here that it was maybe about 0.5. And then we have the range, which is the distance at which it starts to flatten out, which we see over here is maybe about 800 to 1,000. Okay. And then we can fit the variogram. So to fit the variogram, we give the variogram from our data, and we specify a model. Okay, so in our model specification, we tell it what type of model we're using. So here I'm using a spherical model. You give it the sill, partial sill, 0.6. You give it the range, which is 1,000. So start flattening out towards 0.6 at about 1,000, and then you give it the nugget as well. And it will then tune those parameters so that it fits nicely. So you can see over here, here's our variogram. We're going to say that our sill here is about 0.6, our range is about 1,000, perhaps a little bit more, a little bit less, and our nugget, our y-intercept, looks to be about something small, so I'll just put 0.1. Okay, it might actually be about 0.05, I suppose. And then the fitting routine then goes and estimates the best fit to the data, and you can see here that the sill is 0.05, the nugget is 0.05 at range 0, and the sill is 0.6, near enough, which is what we guessed, at range about 900. And you can see that it fits the data reasonably well. And so now we can interpolate. We've got a formula that relates the gamma to our distance for any distance. So we can now apply that across our region, no matter where we are, no matter what the distances are. And how do we do that? Well, it turns out that we do that in a way such as we want to minimize the variance in the estimate that we're putting in. And with a bunch of mathematics, we can show that the weights are determined by solving a system of linear equations. This is the system of equations. So you can see here that the weights must add to 1. That's an easy one. And here you can see that the weighted average of the distances between pairs, it's got to be, we want it to match up with the, for the covariance between pairs, has got to match up with the covariance from our location, location that we want to interpolate to each of those points. So we essentially want to match those two covariances up. The mu is basically a constant that's introduced in order to solve the equations. Basically, it's called a Lagrange multiplier. You can click the link if you want to read about those. But basically, essentially what happens is that this here is a simplified, it's sort of a simplification that occurs after you introduce the Lagrange multiplier. So the original system is actually quadratic, a quadratic equality in the weights W, in the unknown weights, and you introduce this additional constant in order to simplify it down to a linear system, which we can then solve with a bit of matrix algebra. So once the WJs are determined, so for a given X, we determine the WJs, and then we can then determine the Z hat value just by using the same inverse distance weighted average that we had before. You remember that before we had a division here by the sum of WI. Well, we know that that's actually equal to 1, so you're dividing by 1, so we can get rid of it. Okay, so solve that system, chuck the W's in here, and that'll give you Z hat at each point. Repeat the process over the entire region. We do that with the Kriging function in GStat, and it takes the same form as the IDW. So it takes our formula, it takes our set of locations that we've sampled at, it takes our set of locations that we want to interpolate to, and then it takes an additional parameter, which is the model that we want to use, which is the variogram model that we fit back here. So it's that model there. So it's that trend line there. Okay, it gives us the same output that IDW does, so it'll give us a spatial object which is the same as the grid that we've put in. It'll have the same locations, and it'll have two columns for the prediction, which is the interpolation value, and the uncertainty in that interpolation. So because we've built this using a statistical model, we can estimate the uncertainty in that statistical model, and therefore get a measure of how much uncertainty there is in our prediction. And we would expect to have low uncertainty at the observations that we've sampled. So near our sampled observations, we would have very low uncertainty there because we know what the measure is, right? The only uncertainty that we'd have would be associated with the nugget, so that which is estimating the variation at a point. So that's the variation in the measures taken repeatedly at the same location. But the further we get away from our sampled locations, the more the uncertainty we'll have, particularly if we're extrapolating. So if we're moving between observations, the uncertainty will increase, but it won't increase too much. But if we're going past observations towards regions in the areas of the region where we have no points, then our uncertainty will get quite a bit higher. So here's a Kriged version of the zinc. So you can see here's the model fit, and here we're plotting it in the same way as we plotted it for IDW. And you can see here that we get essentially the same surface, but it's much smoother because we've used a statistical model underneath it. Okay, and so we get these increased zinc near the river and also in some other areas, which is interesting. So perhaps these are near where streams are, perhaps, or different soil composition, maybe. Clays and silts that allow, some of them might allow heavy metals to go into the soil a bit more, perhaps. So it could be the type of soil or something. And then you've got regions with low zinc concentration, which tend to be further away from the river. When we look at our uncertainty, so instead of plotting the var1.pred, we're going to plot var1.var to get the uncertainty, and you can see here that the uncertainty is low wherever we have an observation, so that's the darker points, and uncertainty is highest in areas that we have no observations at all. So we're extrapolating over to here, and so because we're extrapolating, we have quite a lot of uncertainty in that extrapolation. So in these areas that we haven't measured at all, we've got quite a bit of uncertainty, whereas in this area here, where we've measured around it, we have less uncertainty because we're just interpolating there, not extrapolating. Okay, so that sort of makes intuitive sense. Now, with universal kriging, we add another stage of modelling. So we noticed before that the log zinc concentration was highest next to the river and was lowest further in. And so in that situation where we know that we have distance to the river, which we can measure everywhere, we know it everywhere on our grid location, right? Because we can just simply measure that. We could use that to predict the log zinc concentration and therefore do a better job of our interpolation. Now this only works if you have a set of covariates that correlate well with the thing that you have only measured at certain locations, and you've measured that thing everywhere. So for example, if something correlated with climate variables, such as rainfall or forest cover and all that sort of stuff, then you could totally use that to predict spatial trend because we have that measured everywhere on the planet. Okay, we get that from spatial, from aerial photography and so on. We can get ground cover, forest type, and all that sort of stuff. So we have that everywhere, so we can use it. Similarly, things like elevation, we have everywhere, and we can use it for our spatial interpolation. As long as the thing that we're measuring correlates reasonably well with those things, we can take advantage of it. So if you have that sort of thing, that makes sense to use it. If you don't, then it makes sense to not try and use it, right? So simple kriging is often the best thing to do in many situations, unless you know that you've got a set of covariates that you've measured everywhere and that will correlate well with the thing that you haven't measured everywhere. Now, on top of just fitting a statistical model, we then do kriging in order to allow for that spatial correlation. So it's sort of a multi-step process. What we do is we take our observations and we just use a standard statistical model in order to estimate the outcome variable at the locations that we've measured it, conditional on the covariates measured at those same locations. So we've got a bunch of covariates, we've got our outcome measure, we fit a regression. That's the idea. Okay, and then we take that modeled average and we predict over the entire region. Okay, we've measured those covariates everywhere, not just at the locations. So we can then predict from the model, right? The model gives us basically a formula that relates the outcome variable to all of the covariates. We can use that formula with everywhere with the values of the covariates to predict what the spatial trend would be. So that's step 2. We then say, okay, we've taken care of the spatial trend, so now we'll subtract the spatial trend away from our observations to give our residuals, to give our leftovers, because the trend will be an average, so it won't be capturing everything in our observed values. It'll just be capturing sort of the average in that spatial location. So it'll be a bit out, right? And so we'll have some leftover information in the residuals. We then use simple kriging on the residuals, and then the simple krigged surface from the residuals and the statistical model prediction are then added back together to give the predicted spatial trend. Okay, so let's see an example of how we do that. So you remember that log zinc concentrations were highest when they were closest to the river, and we can just confirm that just by plotting the log zinc versus the distance to the river. Okay, and so you can see that sure enough, as the distance increases, the zinc concentration drops off. Now we want to fit a statistical model to this, and the only thing that statisticians know how to fit really is a straight line. That's not quite true, but it's a good approximation. So we need to turn this into a straight line. So at the moment you can see it's got a bit of a curve to it, and we can do that by square rooting the distance. So we do a bunch of transformations such that we force it so that it's a nice straight line. So you can see here that zinc reasonably in a straight line fashion decreases as the square root of distance increases. So we can fit a straight line linear model to this. So there it is there, that's the model fit, that's the model formula. So log zinc is about 7 minus 2.55 times the square root of the distance. So you can see when the distance is 0, the log zinc is about 7. And when the distance increases to 1, which is out here somewhere, then the log zinc concentration would be about 7 minus 2.55, which is about 4.5, which is sure enough what the line is telling us, right? So we use the LM function, short for linear model, for that. Some of you may have seen this, some of you might not have. Don't worry about it too much. We're just going to be using it as an example, and you'll see how to fit that in the workshops. And we could use whatever sort of linear model we like here. So we don't just have to have one covariate. We could have a whole bunch if we want to. Okay, so that often happens, for example, if you're looking at things that are related to climate. So there's a sort of a standard set of climatic variables, sort of 17 of them or something like that, that are available essentially across the planet. And often for things like predicting the niche of various animal populations, for example, it has a lot to do with climate. It has a lot to do with other things like human population density and all sorts of things. And so you may want to put all of those variables into a model. It needn't be a regression model, it might be something more complicated. Okay, but that's the basic idea. So we have some statistical model that we can build that allows us to predict a log zinc location, the log zinc value at any location. So here's our prediction. You can see that it just depends on the distance to the river and nothing else. So anything that's about the same distance, like here, is all the same color. Okay, and that color in there is similar to that color about there, right? Because it's the same distance from the river. So this is a very poor prediction because we're not accounting for any spatial correlation at all. We're just accounting for spatial trend. Okay. So we then subtract this trend from the actual values so that we get a set of residuals. Okay. So the set of residuals are essentially telling us that, at this location here, we predicted, because it was quite far from the river, that it would have a reasonably low zinc count.
zinc concentration, but in fact it had a higher zinc concentration, so its residual was a fairly large positive number. And similarly, you get this sort of area through here where perhaps there might be a wee stream or something, or a lower area in elevation, or perhaps a soil or something or other, where we've got a series of positive residuals. So this is saying that we've underestimated the trend here, because of course they're all far from the river, right? So we've assumed that the concentration is low, because that's what it is on average. In other places close to the river, we've underestimated things as well, down here. So there's, we haven't got it right with our spatial trend. It's not perfect. So there's some underlying further trend which we can then Krig. Okay. So essentially we work out the residuals and we Krig that, simple Kriging of that. So we fit a variogram, same way as we did before. Here, notice that the sill and the nugget are a bit different. So the sill's now only about 0.22 or something. The distance is maybe a little bit smaller. It's probably not too different. And the nugget looks about the same. It's a little bit higher than it was before. Okay, and then we use the Kriging function to interpolate across the region. Right, so this is finding areas in space where our statistical prediction from our linear model is consistently low. So here's that region through here and the region through here where we were underestimating, so our residual was high, right? And now we add that back to our prediction to get our final surface, which you should see looks something similar to the surface that we generated before using plain Kriging, simple Kriging. The difference is that because we've accounted for the spatial trend, our uncertainty from our Kriging is much lower. So you can see when you look at the uncertainty plot, it only goes up to about 0.2, again in the regions that we haven't sampled, where we're extrapolating to, whereas before it went up to 0.5. So by using the external information in the distance from the river, we've managed to explain a bunch more of the spatial variation, so we've got less variation left over, if you like. So to sort of summarize, before we do that, how do we do that in practice? We don't tend to follow those 5 steps in practice. The computer does that for us. So we can just put our model formula, which is our linear model formula, directly into the variogram and Krig functions, and it will take care of fitting the linear model, taking that out, and just looking at the residuals, Krigging the residuals, and then adding the model fit from the linear model back in. Okay, so the only thing we need to do is establish the formula. So that's just looking purely at the location data. So it's like this, right? Purely looking at stuff like this in order to construct a suitable model. So it's standard statistical modeling stuff. So we construct a statistical model for the outcome variable at our locations, given covariates that we can use over the entire region. And once we've constructed that model, we figured out what a best model is, we can just plop it in here and it will take care of the Krigging for us. So to summarize, inverse distance weighting is useful mostly in the case where the points are relatively uniformly scattered across the region, right? Because it sort of does that global smoothing. Okay, so if you've got a great amount of heterogeneity, so points are not randomly scattered across the region and that they're clustered a lot, then Krigging is probably the better way to go. In fact, I would argue that Krigging is probably the better way to go anyway, because it gives you an estimate of the uncertainty. The disadvantage with Krigging, of course, is that you do have scope to fiddle about with the variogram. So you've got to fit the variogram and choose a variogram that makes sense for the data that you have, and that's not necessarily a simple task. There's a particularly if your data size is small. So we'll see a little bit about that in the workshop. Universal Krigging then is what we do when we have a parametric model for the underlying trend. So if you've got a bunch of covariates that you've measured everywhere, and those covariates are useful for predicting the measure that you haven't got everywhere, you've only got a set location,
As long as the correlation is pretty good, then you can use that information in order to reduce the uncertainty in your Kriging. Okay, so you should do that if you have covariates. If you don't really have covariates, or they're not strong, or there's not a clear correlation, then maybe sticking to simple Kriging might be better. That's it.